Southern California Splunk user group meeting. There it is. I'm Sean Ruthier, customer user group leader. We have Dave Urban also on the line. He is our Splunker in charge. And we also have Micah, who's going to be presenting on machine learning today. So next user group meeting is Tuesday, August 25th. Our topic is to be determined. September the 22nd, I'll be doing a preview of the talk that I submitted for Conf 20. And then in October, we'll be skipping the user group meeting due to Conf. If you're interested in presenting in August or November or beyond, feel free to drop David a line and we can get you queued up. We have a Slack channel, and new to this month is now we have a YouTube channel. So going back a few months, we've been recording these sessions, and we've put the last 3 up on YouTube, and we'll be putting this one up on YouTube as well. So if you don't have a chance to get to the user group meeting the day of, feel free to go to the YouTube channel and catch up on it. Conf is the 20th through the 21st, and it is free attendance. So be sure to get anyone who's interested in Splunk queued up for attendance. So with that, we'll be kicking it off to Micah. Thank you.
Thank you very much. Happy to see everyone this afternoon. I'm looking out at the sea of participants and recognize a lot of names. So this will be a good time indeed. If the group is not interactive, then I'm just going to do this session again next month since we have an open agenda. So just be warned of that. Per the introduction, my name is Micah Gaither. I'm a sales engineer here down in Southern California. San Diego, more or less, kind of on the outskirts. So if you're in the area, I'm in Valley Center. You might be familiar with that or not, but San Diego, let's go with that. I've been a Splunker for a couple years, about 2.5, and it's been awesome. I in a former life was over at VMware doing some customer analytics, but had great challenges operationalizing it. And when I got my hands on the machine learning toolkit in its early stages and an opportunity to come help customers with it here at Splunk and other premium solutions as well, and core and cloud, I jumped at it. So here I am today and happy to be here. So I'm going to share out my screen if that's good with everybody. So I'm having some bandwidth issues today. I'm actually talking to you a good old Google Voice. So you won't get to see my video, but I'm not that handsome anyways, so you're not missing out on anything. How's that resolution coming through?
We're not seeing anything yet.
Okay.
Audio sounds fine though, Micah.
Yep.
Oh, thank you. How about now? It says I'm sharing.
Yep,
Good.
good now.
I get like confusion going from Zoom to WebEx to Teams to you name it, but nonetheless, here we are. So I kind of thought today, and what I do a lot of times is I run through silly ML exercises with the team, usually like classification exercises that are quite goofy, and then I get strange looks from the audience. For an example would be the Titanic data set, right? Based upon the data, the manifest of these passengers, we know who lived and died. So let's put in ourselves on this manifest according to a data dictionary and figure out if we lived or died, right? So stuff like that. But reason got a hold of me, and I thought, I better slow down and make sure we're all on the same page first, because what I'd really like to do is invigorate us as a collective, kind of an ML collective here in Southern California, right? Leveraging what core can do, what the premium solutions can do around ML, ITSI, UBA, ES, but also the MLTK, right? So I kind of want to level set with the audience and make sure we're all kind of in the same page in our journey, and then go from there. I like to start off with some discovery, kind of some foundational. I'll skip through a lot of that if we're all pretty familiar with MLTK already. MLTK 5.2, I think really got kind of not as much visibility maybe. There's some good stuff in there. So I want to show you that. And then a G-means example, because that is part of the new 5.2. I think it came out like mid-May, but I don't know. I think COVID and everything, like everything else, got kind of swept under the rug. Is that good with everyone? And I'll get you out of here for Taco Tuesday. I promise. I'm taking that as a yes.
Yeah.
I was going to say,
All right.
It's a slow walk to the kitchen. It's a slow walk to the kitchen for tacos and beer, man. So, you know.
Yeah. Well, hey,
That's not saying
get
much.
your beer now. You don't have to mute, pop in a bottle or a can, either way. This is my slide to stop talking. And I put this here because, again, I want to understand sort of where everybody's at as far as machine learning goes. Some of you may recognize this. I'm very much dating myself, this assembly here. I make no claims to understand what it's doing other than the sleep command or the wait, but this is a sleep function that I'm telling myself to stop, figure out what's going on. Is there anyone out there that has, a good familiarity with machine learning toolkit? They've operationalized it. They've got some models built, and they're kind of using them either in production or maybe just in a lab or sandbox, and they're maybe pre-prod, kind of a UAT. Okay, that's fine. Does everybody know sort of what the machine learning toolkit is and why we have it, why it's important, and why it's so awesome?
That's what I'm looking to get out of this, to learn how to use it.
Deal. Okay. Okay.
Yep. I was going to say, I'll add to that, Micah. We've got it, deployed here in our space, but we're not getting much traction with usage because we don't have data engineers deployed in all the teams that are leveraging the tool sets yet. So it's kind of a hard model to consume if you're not data focused like that logic, right?
Yep. No, I hear you there, and I'm going to show you a few things that may or may not help accelerate. So let's kind of start with a high-level overview of MLTK, right? Some foundational stuff, and I'll zip through this pretty quickly. But MLTK is the app alongside Python for scientific computing, which is our Python interpreter, that really enables you now to be the citizen data scientist. Typically, right, you would need, if you're going to do ML and Splunk, you need to have some Splunk skills, right? I need to know a little SPL. But I also need to know a little bit of data science, right? At least some descriptive statistics to work my way through. What algorithm would I use for which branch of supervised and supervised reinforcement type learning? What we're doing is accelerating you with MLTK. You are already domain experts for your data, right? You understand this data, whatever the use case, is better than anybody else. So how do we accelerate you to get value out of this data? That's where MLTK comes in, right? Let's abstract a lot of the obscure data science and the math, right? If you want to go there, you can, right? We have that capability. It's all Python on the back end. There's a deep learning toolkit if you're interested in GPU, neural networks, that kind of thing. But let's just get something operationalized for you, right? Let's get you using the thing. And here's why it's so powerful to me, is it sits right on top of Splunk, cloud or enterprise on-prem. It's SPL underneath. There's no pivoting to an analytics workbench. You're still working out of a search head. So you're taking that data that you already know and love, you're so familiar with, you're going to pick an algorithm, you're going to fit that algorithm to it to create this model. That model, this algorithm, is coming from Python from scientific computing, which I mentioned is our Python interpreter, but it's all the Python libraries that folks know and love, the NumPy, SciPy, scikit-learn, stats models. Right? We're not recreating the wheel here. So when you say, well, Micah, what about this algorithm? It's out there. Bring your own algorithm. I have no doubt, right? It's not a black box is the point, right? So we apply this Python to your data to create a model, and now we can apply this model to your data as it comes into Splunk, as it's been ingested into Splunk, in a near real-time fashion, right? That is Splunk, right? And this model persists. It's transportable. We can partially fit it, iterate through updating the model as the data comes in. This is all through this Python for Scientific Computing and the Machine Learning Toolkit app itself. I actually come back to here because these links are pretty good. If you ever check out the documentation, I just shimmed these in here. My slides are horrid. They're left to my own devices. But take a look. Take at the algorithms that come out of the box and the scoring metrics out of the box. And then there's always an MLSPL API to which you can integrate, like a Jupyter Lab notebook or something like that if you want to get interesting. One of my favorite parts about NLTK is, hey, in this data pipeline, if you want to do it all through a combination of Splunk and NLTK, do it, right? But a lot of times you have other tools, right? Tools that data engineers are familiar with, and you're not going to pry out of their hands. That's fine, right? So do the munging, do all the pre-processing. We know that's the majority of the work, right, for these data engineers, data scientists, et cetera. Do that in Jupyter Lab, Notebook, whatever you want to do, that's fine. Detail your heart out. If you want to visualize, you want to operationalize that data on a dashboard, an executive dashboard that's in a CMS system somewhere, that's fine. You can use us to run the algorithm against the data that comes in real time, and then use the tools that you already have in your environment and leverage those. That's quite all right. I actually just saw this example yesterday, and I thought it was really cool because I was working with a customer on embedding a Splunk dashboard into a CMS system that they have. So if I scroll down, you're going to recognize this, right? That's Splunk. This is Splunk. We can tell right away, right? So you can create your dashboards, your panels, your reports. That's no problem. You want to put them in an external website, do it. If that's what gets people looking at it, using the data, taking action based upon the data, the model that you've created, absolutely. I won't beat that up anymore. I always show this because it's very, very important to be mindful of the MLTK version and the Python for Scientific Computing add-on, which is required, that compatibility there. So I think you can figure out the matrix on your own. It's pretty simple. But basically, if you're going to be on 8, you're going to run the 5 series of MLTK and the 2 series of PSC. All right. I will do a call out though. Upgrading the Python for Scientific Computing may require some retraining of models depending upon the algorithm selected. So if you're on 7 and you start building awesome things and you plan on going to 8 in the near future, which you probably should, you may need to retrain those models. Keep it in mind. All right, this is what I want to get to though. 5.2 came out, I want to say mid-May. Someone keep me honest there. There's some good stuff in there. Really, really good stuff. One of them is this G-means algorithm for clustering. So I think a lot of us are probably familiar with the K-means algorithm for clustering. G-means is based upon K-means, similar to X-means, but it's different in how it works. And that there's a statistical test that it uses to identify the number of clusters. Whereas I'm going to show you when we go into MLTK, you have to input the number of clusters to run the K-means algorithm. G-means is going to do it for you through this statistical test that I mentioned. So it's really a hierarchy. I'll show you. I won't do it now. But this K-means, the smart clustering, the smart prediction, it's all in these smart assistants that I'm going to show you within the MLTK app to get you going right away out of the gate. I'm going to show you a couple examples, and hopefully you turn around and start doing them on your own. You're still motivated after you see how simple this is to start leveraging the data that you have in your system today. Other cool things in 5.2 is, so the auto prediction algorithm, right? It's going to determine categorical and numeric all on its own. There's a density function algorithm, supports partial fitting. That's pretty neat. You don't have to retrain the entire model. And just as a kind of afterthought, this heat map plot down here. So you do something supervised, you're doing a classification project, and you've got a confusion matrix at the end. You have a nice heat map plot for it. So let me show you this stuff. Enough of my slides. No more. Slides be gone. The slides are more from me than you to keep me on track. It's a good thing. All right, so let's go into Splunk as we know and love, right? So you'll see, I'm just running this on my laptop. I mean, literally, you know, you've got Splunk running somewhere on a VM, wherever. Load up Python for Scientific Computing. Load up the MLTK app. Simple. It comes out of the box with these showcases that you can use as examples, right? We can do it by operation. We can do it by industry. I'm going to show you a little clustering today because I think it's a great way to get started. I'll do customer workshops from time to time, kind of MLTK 101. Let's get, you know, let's define a problem and go out and solve it. Sometimes you don't know what the problem is, right? What are we trying to do? Well, I don't know. I just want to do ML because the cool kids do it. Fair enough. I love the admission. Let's start clustering the data. Let's start exploring the data, right? That's where our descriptive statistics come in. Let's explore this data, and the question will come to us, right? Because we're going to go, why is that that node so far away from the others in this cluster? What's going on with that? What are the attributes? What are the feature sets that make up that outlier?
Hey, Micah, can I ask a quick question, man? Because I keep hearing this. Just fire it up and give it a try. But doesn't it require certain types of sets to be available? Because, you know, we fired it up and give it a try, and not much came out of it. So.
Okay. Well, so you're gonna have to trust this isn't a cooked turkey. This is a raw turkey here that I'm cooking all the way for you today. That's what I'm going to show you right now. Is when you install this app, and this is, you know, latest greatest 5.2. It comes with a bunch of canned data already. There's CSV files that are bundled with it. So they're just lookup files.
Fair enough. But I'm talking about, you don't just lay down the ML toolkit on top of your current infrastructure and say, wow, look at all this value that's coming out of it. It still requires a little bit of work. Right? It does. Yeah, it does. But that's where, you know, kind of that Venn diagram. I took that slide out. But there's that Venn diagram of someone knows the data science part of it, the stats, ML, et cetera. There's someone that knows Splunk, and there's someone that has that domain knowledge, right? So I can come in and I can help you, and I say, hey, look what I see. There's high utilization over the weekend. I figured something out. And you go, no, Micah, we're doing maintenance, or it's into quarter. Knucklehead, of course. Oh, that's fine. But you got to have all three parts of that Venn diagram to make it work. Sure. I don't think, I'm not trying to shoot in the foot. I'm just saying I don't think you want to underscore the importance of that, right?
Yes, very, very valid. Yeah. But at least within the showcase, these experiments, you know, taking in these canned lookup files, choosing an algorithm, applying the algorithm, creating a model, and then starting to think, man, how can I apply this to what I have today? It gets the thought process going. I really think so. And so I'm going to show you here this experiments here, these smart assistants. Actually, let me backtrack a little. Let me show you how we did it in the showcase before we had the smart assistants. And you're going to go, oh, it's even easier. So again, I'm a fan of this hard drives data set because it's pretty large. And I'm a IT guy by scars. So drives failing. I think I still have nightmares of the old days and mirror sets are broken and stuff like that. The smart drives, self-monitoring, analysis, reporting. I think it's technology. I don't know. I think it's technology. So this is how we do it in the showcase. And the showcase it'll bring this data in and it'll get you a pretty good start. You can see, right, it's just a lookup file that we're doing. This disk failure CSV is included with the app. I know for a fact there are some null values in there, and there's like 8,000 results. So we'll just take a sample of 1,000 to save ourselves a few cycles. And so in this example, this clustering of numeric events, you kind of have to know a little bit about, well, just that, clustering numeric events. So we lay out that using this k-means algorithm, it's very sensitive to scaling. And let me take a step back, right? So this k-means algorithm, what it's doing is, so this is an iterative algorithm. It's trying to partition this data set into distinct non-overlapping subgroups, well, clusters, right? So each point, each observation in the data, it only belongs to one group, right? And so it's iterating through trying to make these intra-cluster data points as similar as possible while keeping the clusters as far away as possible. Pretty complex, pretty awesome, right? But if you think about it on just one space, if you think of like a scatter plot, right, and I have a line of best fit that's going through all these observations, right, and I'm measuring the residuals of those, I'm summing the squares. It's very, very similar to what k-means is doing in a way, and then I'm trying to minimize the sum of the squares from these observations to the centroid, the center of that cluster. It's awesome, right? Awesome that we have this available to us. And so the way we're going to do that is some pre-processing. And again, part of this you kind of have to know, right? And that's how it was with the showcase. So let's start from the beginning here. I know I need the standard scaler, right? If I look at my data here in the preview, right, smart 1, 2, 3, 4, 5, they're all over the place. So I know I need the standard scaler. And I'm going to select these to be scaled. And I'll apply that. I'll take a swig of coffee. That was a swig of coffee in real time. And now what I'm going to do is this principal component analysis. So all right, we're getting a little mathy again. Hang on tight now. So I just did a standard scaler across these 5 fields or features. The standard scaler creates 5 new fields that are now scaled. Ta-da. Here's what I'm going to do with the principal component analysis. So this principal component analysis, its reason for existing, and by the way, this thing was written in like 1901. I mean, this stuff's been around for over 100 years. You imagine that math? What we're doing is reducing the dimensionality of this data set. So I'm going to go from 5, the 5 that I just created, down to 3. Why 3? Because I know I want to plot this in 3 dimensions. Spoiler alert, right? But that's how I'm going to explore this data after I've clustered it all. So this, I'm trying not to get too nerdy because I can't get that nerdy. This principal component analysis is reducing the dimensionality of this data by orthogonally transforming this collection of data and finding a best fitting line across the data, and then another best fitting line perpendicular to the first line that we created. So vectors, right? And it's going to repeat this process, this orthogonal process, until the dimensions of the data are highly uncorrelated. So we're looking for high variance. And that is how we're able to reduce the dimensions from 5 to 3, not huge, but we're minimizing the information loss in reducing those dimensions. So if you think of like data sets that have many, many, many features, hundreds of features, right? I'm looking for correlation and variance across those. So I want to look for high variance, reduce them down to a number of feature sets that it's manageable. It's not hundreds, right? In my case, because I'm plotting it, I need 3 dimensions. I need an X, Y, and a Z. Stay with me. Stay with me. All right. So I've applied my principal component analysis. And I bet you knew what was coming. I have 3 new fields, 3 new principal component fields. Ta-da. So I'm going to select those fields because that's what I want to run that k-means algorithm against. The 3 principal component fields I just created. Reduce those dimensions. Now, here's the thing with k-means. You have to know the number of clusters. It's an input. There are ways statistically to determine that. You know, there's something called the elbow test where you can look at kind of diminishing returns as you increase the number of clusters. But in this case, we're not going to go there. And more or less, you iterate kind of, and even that's subjective in some ways. But you iterate through there with the number of centroids. But I'll do 3. I've seen the data. I peeked. you know, 3 is not the right number, but it's close. It's ballpark. And we'll run this algorithm. We'll create this model. Here we go. Here it is, coming in. Right. So now I've taken my 3 principal components, these 3 dimensions. I've clustered. Across the principal components. Stay with me, laptop. And here we go, right? So I have my principal component 1, 2, 3. I've got my clusters, 1, 0, 1, 2, right? And now I can iterate through and find, you know, what is the correct number of centroids here, trying to minimize, you know, just looking at it, right? If I've, you know, from the use case of these hard drives failing, I would go, who are these 2 knuckleheads? What's going on with these guys, right? I would investigate them right away. Why are they so different from their peers? You know, and so, you know, pick a data set in your environment, right? What else could you apply here, right? Maybe it's individuals. I'm up here somewhere. Why am I so different than everybody else now? Right? But this could be, you know, user behavior. Absolutely. You know, user behavior analytics for sure. Okay. What's great about this, and I was going to not pull this out right away. I was going to save it. But what is so powerful about this showcase and doing it this method is that the SPL is right here for you. Right? So every step along the way here, I can look at this SPL and apply this SPL now to my data sets, right? So it's a quick way to start reverse engineering, right? Through that showcase, through these showcases here. Pick a use case, pick an example, and start working through it and reverse it. Now check this out. So this is the smart assistant, right? This is the next iteration now of getting you moving quicker, faster, stronger, something like that. So we'll do our smart drive friends again. Actually, let's not. Take a step back. It cannot help me type. Not yet. I know there's a Bitcoin data set in here. It doesn't need any pre-processing, so that's going to save us some time. Because the point is, look at what the Smart Assistant is doing it for us now. So step 1, we need some data. Let's get some data in here. Right, so we can do it via search, right? Standard Splunk search. If you want to look for some lookup files, data models, transform file. These are all the ones that are included in MLTK, and then some extra ones I've got in here for like some NASCAR stuff that I do on the side. This is new. Metrics, right? You can come out here and grab some metrics. Where would some metrics be? There's some metrics in here. Okay. So it's easier. I'll quit saying it's easy. It's easier now to just get the data ingested, right? I know I want some Bitcoin data. Here it is. Right. Likewise, I could have typed Bitcoin in here. But here's our data set. Super simple. Not a lot of features here, right? I'm going to do another k-means. So remember what we just did, right? In this case, I don't need to do any pre-processing, right? I'm interested in from to value. From to value. Cluster. It's k-means. You have to put in a parameter for the number of clusters. I like 3. So that could be where maybe you go to a Jupyter Labs notebook, right? If you want to do some statistical testing to figure out what would be a good starting point for my k-means. Right. 2 from. Give me value. There it is. We're clustered. Right, so I left out all the pre-processing. In this case, we didn't need it. But quickly, we get to, again, understanding that there's some outliers in this data, right? I might even look at this data and make a determination that, hey, I might group these differently down here, but I would maybe be looking for a cluster up here. What's going on with these rascals here? Large Bitcoin transactions compared to all the minuscule ones that are typical. Does that make sense? The smart assistant, getting us going faster than the showcase examples there? And again, simple SPL, right? Simple SPL. Bringing in my CSV. I'm running this fit command against this algorithm and providing these fields, 3 clusters, and then I create a model. This is a draft model in this case. All right. Let's take it one step further now. Here we go. We're gonna bump this up. You'll notice. Let me show you this since this errored out on me. Someone's going, Micah, what you doing over there? It's memory on my laptop. Sample command. Use it. Remember, I used that on the original k-means. I should have here. Yeah, there's only 100,000 results, right? Okay, so it's bust out of the Bitcoin. Let's go back to our smart drives. So I still have this experiment out here, this SoCal Bitcoin, to which I can compare models. I can compare those silhouette scores. As I create a new experiment here, SoCal smart drive. What I'll do is I'll just use the Splunk search. To pull this data in. Again, I know there's some null values in there. I'm going to do a sample size. Break this down. All right, so now we have the 1,000 results that we're expecting. Same process, define the data, let's go and start learning the data. My scalar. Micah, we know the scalar, I know. Let's do the scalar, all right? You want the mean, standard deviation. We know we want our PCA. We know we want our principal component. Same thing's going on. But watch when we get to the end now within the smart assistant. Same deal. I want 3, X, Y, and Z. Okay. Now we're going to cluster principal components. You know what I'm going to do? 3. Fire. You can do it. Come on, laptop. Here we go. You want PC1, PC2, our friend PC3. There we go. Again, we've got some outliers here that I'm interested in, right? So same kind of observations. In this case, actually, this sample is a little more interesting, right? Because we just had a big blob and then like one guy hanging out. A lot more outliers over here. And because I did a smaller sample set in this run through, I actually get my silhouette score. So the silhouette score, if you think of it kind of like an R-squared in a regression problem, the closer you are to 1, the more cohesion, the more cluster separation there is in this model. It's a sum of squares at the end of the day, or a Euclidean distance from the centroid to the observation. But short is you get this to 1. So I would continue to iterate to these number of clusters, right, until I get something that improves in the silhouette score. But hey, this is our first try, and I like 3. In any dictionary. But look what I can do now here in the smart assistant. So I've got some good stats, right? I can come through here and start digging into this data, but I can also look, I can mark, well, what is an outlier to me? What is the intra-cluster distance that I'm interested in this distribution? Right? So if I'm just indiscriminately speaking 64, right? But if that cluster distance is greater than 64, it's an outlier, right? I have now some action I can perform on these outliers, right? I couldn't do that before. I mean, I could. It wasn't as simple, right? But I can move this outlier detection back and forth, and now I can act on it, right? Now I can schedule the model training through this menu a lot easier. I can create alerts, right? We all recognize this. Create alerts in Splunk, right? Come in here and create our actions. We can set thresholds. How many outliers over a certain time span? And I can now operationalize this model that I created here this afternoon with you. It's something that's actionable for all of us. Does that make sense? Am I out of my mind? Well, I could be. All right. So I'll show you one more thing, and then I've got some questions for all of you. So get your mute buttons ready. So again, it's all SPL at the end of the day, right? Like I was kind of bragging about it, right? This is great. We don't have to pivot to some other. This is the analytics syntax, the language that Splunk uses. It's SPL. We're abstracting the Python for you. We're putting it together in these nice assistants for you. But look at this. You see it's something a little different, right? If we walk through this, again, I'm loading my data. So I'm going to fit this pre-processing stuff to these fields, right? And I create some models for them. That's really easy to kind of just naturally follow. What's different here? That's not k-means anymore. Right? Remember, I kept doing k-means, and you got tired of me saying 3 for the number of clusters. This is g-means. It's new in 5.2. So g-means, much like x-means, which has been around prior to 5.2, it's similar in the case that it will determine when to split a cluster for you. So there's no parameter that I'm adding here. I'm not adding my number of clusters, k equals 3 in this case. G-means will figure it out for me, right? G-means does this Anderson-Darling statistical test where it's looking for, hey, if this data set looks bimodal, I'm not finished splitting it yet. When it looks Gaussian or closer to a normal distribution, I'm probably there, or I'm close to being there. And you can tune this Anderson-Darling statistical test if you're so inclined, but or you can just run it as. But the point of it is using both the showcase and that smart assistant, I can kind of reverse engineer, and now I don't have to run k-means anymore. I can just change my SPL, pull out that parameter, and run a g-means. I can run an x-means, right? I can go to the documentation, the Splunk documentation, look at the algos that I want, and start working through them, and start looking at silhouette scores. Which one is performing the best against my data? Right? Here it is. And you'll see, boy, it heavily, heavily clustered the data. G-means. Right. But I've now got this model that persists that I can start looking at. In this case, look, 34 clusters. I got the first 3 right. That's about as good as I did. 34 clusters recommended for a G-means for those smart drives. Pretty neat, huh? Pretty neat. X-means is the other one I was talking about. Same thing. Same thing. You don't have to specify the number of clusters, which is nice. It uses a different statistical test, this Bayesian information criterion, or BIC, B-I-C. You'll see that a lot. And I can't even begin to describe what it does. But again, it's enough that you and I, who aren't hardcore, you can do this, hardcore data scientists, we can go in there and we can just, what does the result look like? What does the accuracy of my clustering look like? That'll get me most of the way there, right? And then I can pull in someone who's a real ML engineer maybe to help me fine tune this. But it's at least impressive enough. They go, dang, you got here on your own? That's not bad. All through Splunk, huh? Okay. So quite a few, the more reasonable number of cluster segmentation here using X-means, right? But that's what it is, iterating through these algos, creating the best model, and then, partially fitting them and continuing to train to improve that model over time, right? So got about 10 minutes left. What I would like to now kind of turn to is, what does the group want to see? Like, what's the group trying to achieve with ML, with MLTK? Maybe it's even ML within a premium solution like ITSI or something. What can we do to help you? You'd be interested in seeing. It's going to make life better for you. And let's make that another session and give you some playback and some good content.
I'll second Quincy's comments in chat, network traffic examples and possible outliers with that.
Oh. Excellent. That's a really good one. So we have a probability density function. There's a state space forecasting, which is those are both really in vogue right now. They would be awesome to see. Yeah, looking for outliers, but also forecast across the data. Super. I would like to do those. Okay, I mean, we could start there. Information is available. Reach out if you want to talk MLTK, you're working through some science experiments on your own, you want a little help, collaborating. Let's do it. It's a kind of a passion project for me. I enjoy it. Hopefully you noticed today. And let's have some fun. So Taco Tuesday, initiate virtually. Thank you, everyone.
Awesome. Thank you, Micah. And thanks, everyone, for joining. We'll see you again in August.